Hi, I'm Dr. Bill Cordua. I'm a geology professor at the University of Wisconsin-River Falls. Today I'm at Interstate Park, a fantastic state park that spans the St. Croix River between Wisconsin and Minnesota. There are plenty of opportunities for outdoor recreation here in the park, including rock climbing, hiking, camping, nature walks, and a variety of other things. But there's also some fantastic geology to see if you examine the bedrock in the area.
There are also some terrific rock exposures which tell of erupting billion-year-old volcanoes and invading seas 500 million years ago. In this show, we're going to be on the Wisconsin side of the river, although these relationships can be seen on both parts of the park. The dark rocks along the gorge are old lava flows and are easily seen from many park trails. At this point, we can see these rocks have circular potholes drilled into them. The potholes were caused by surging water from melting glaciers and the periodic release of water from ice-dammed lakes. As the water swirled over the rocks, boulders began rotating around, getting stuck in low spots on the rock's surface. Once the rock was trapped, subsequent floods would spin it around again and again, progressively drilling these holes. Sometimes you can find the rocks that did the drilling, now rounded to spheres, such as these by the Ice Age Visitor Center. The Visitor Center also has some great displays, including a video demonstrating pothole formation. There are even bigger potholes on the Minnesota side of the river. These are some of the best known in the world. So how do we know these rocks are lava flows? We can see the clues for that better at another place in the park.
We're in a small abandoned quarry that's off the main trails in the park. It's easier to see the nature of the bedrock when it's freshly broken like this and not so covered with lichen. This rock is very tough and strong unless it's widely quarried in the area for use as riprap or crushed stone or other purposes.
Notice they are dense, fine-grained rocks. Lava flows are fine-grained as the liquid magma cools fast, generally not letting crystals grow very large. When we look at these rocks under the microscope, we see they are made of minerals like feldspar and pyroxene that are high-temperature minerals typical of lavas. This particular type of volcanic rock is a common one called basalt. Geologists can study basalts forming now in lots of places, such as Hawaii and Iceland. So we can recognize these rocks easily when we find them in areas that are no longer volcanically active.
Another popular name for basalt lava is trap rock, and it comes from the Scandinavian word trappa, which means stair step. So how did a term like that get applied to rocks such as this? What turns out is these lava flows come out, they are spread over the landscape as one layer on top of another, on top of another, on top of another. And then if these get tilted a little bit, as they are around here, the front of the lava flows show up as steep cliffs, and the back side of the flows show up as gently sloping surfaces, just like a series of stair steps going across the landscape.
Notice the vertical cracks or fractures. These are called joints. Many joints form as the lava flow contracts as it cools. These sharp breaks form the vertical cliffs so popular with rock climbers. The joints also help define the park's signature features, such as the Old Man of the Dales. There are some other clues as to this rock's volcanic origin. These rounded areas are old gas bubbles, gas that comes out of the lava as it flows along and cools. We call these holes vesicles.
Magma has a lot of dissolved gases in it, just like this soda pop. And when the pressure is released on the soda pop, the gas likes to come out of solution and form little bubbles. If we disturb it still further by pouring this into the glass, you see the bubble formation, and notice that the bubbles like to rise toward the top of the container. The same condition persists in lava flows. Only in lava flows, this liquid is cooling so fast that the bubbles get trapped on the way out, leaving the vesicles or empty gas bubbles behind. Those vesicles tend to be more common toward the top of the lava flow and less common toward the bottom. This means when we're mapping lava flows, we can easily recognize the bottom of the lava flow compared to the top, which allows us to get the sequence of lava flows in a particular area and see which lava is piled on top of which. Here's an example of basaltic volcanic rock with lots of open vesicles or gas bubbles in it. This would be very typical of the top of a lava flow. Of course, in Interstate Park, these holes have been later filled with various minerals that reflect different fluids that were able to get into these openings later in the rock's history and precipitate a lot of interesting things.
We call the filled vesicles amygdules. In this case, they're filled with white quartz. Elsewhere, they may contain other minerals such as copper, calcite, and even Lake Superior agates. Here's some basalt from near a flow top, crowded with amygdules. Quartz is the white mineral and epidote the green mineral. There are other ways to recognize flow tops. In a few places you can see these curving structures. They're called ropey pahoihoi. They form on top of very fluid lava flows. Note the lower layer is full of gas bubbles filled with white minerals. Here's modern ropey pahoihoi forming in Hawaii. It's easy to recognize this structure. That's geologist D.W. Peterson taking a rock sample from a 1972 lava flow.
In and around Interstate Park, we can map a number of these lava flows piled one on top of another and all tilted very gently toward the St. Croix River. These volcanic belts are part of a larger volcanic terrain that's traceable all the way from Lake Superior way to the south down into Kansas, although the rocks are buried to the south of here under younger strata.
Here's a map from Roadside Geology of Minnesota by Richard Ojakankis. This large area of volcanic rocks formed about 1.1 billion years ago. Forces at work at that time were attempting to pull North America apart, forming a structure we geologists call the Mid-Continental Rift System. As the rift developed, it filled with lava flows and sediments. Interstate Park has some of the southernmost exposures of examples of these rocks.
I'm on top of Eagle Peak, one of the highest points in the park. This peak is held up by a lava flow that I call the Eagle Peak flow. This is a very long, continuous flow which can be traced for a number of miles and thus is an important marker in mapping the rocks in this area.
The Eagle Peak lava flow has lots of white to pink rectangular grains. These are a mineral called plagioclase, a type of feldspar. They form as crystals in the magma before it gets to the surface. And once these crystals form, they're just carried along by the flow of the lava and then caught up as the lava flow solidifies. Here's another lava flow with phenocrysts. These lighter spots are the mineral pyroxene. Different lava flows can have different phenocrysts depending on the flow's chemistry. Notice also these scratches and grooves. These are glacial striations, formed when glacial ice dragged rocks across this surface. Interestingly, there are also potholes here at the highest part of the park, telling us the ancestral St. Croix was up this high, excavating its valley.
We've seen the volcanic history of the park is well exposed in many outcrops, but that's only part of the story of the geology here in Interstate Park. If we look across the St. Croix River into Minnesota, we'll see another very interesting feature.
As we look across the St. Croix Valley to Minnesota, we see at about the same elevation bands of horizontal buff-colored rocks. These are not lava flows, so what are they? Here's a close-up of these rocks as exposed in the road cut. They're sandstones, much younger than the lavas. So what are they doing at the same and lower elevations as the lava flows? Well, they record the flooding of the sea into this area about 500 million years ago.
That road cut is dangerous to get to because of the traffic, but we can examine that same sandstone on this side of the river if we go walk through the trees and down onto the flank of Eagle Peak. We're down in the woods just a little bit east of Eagle Peak, and here behind me we can see a cliff on some nice layered or bedded rocks. These rocks are sandstone, very different from what we've seen before.
We can see the sandy texture in these rocks. The white bits are fossil shellfish fragments called brachiopods. This is how we know the sandstone is younger, because there were no shellfish at the time that the lava flows came out. A sedimentary rock like this also suggests a beach or shallow water sandy ocean environment with moderate wave activity.
Using fossils and radioactive elements in the rocks, we can determine these sandstones formed about 500 million years ago. Let's say about 500 million years younger than the older basaltic rocks that they're right next to.
Here's some more evidence that the sandstone is younger than the lavas. By the dam in St. Croix Falls, we can see the lighter sandstone deposit on top of the dark basalt lava flows.
When I was field mapping in this area, I found the sandstone outcrops tended to wrap around the older basalts, looking to me like those basalts were islands that were trapped in a rising sea. There's additional clues that might support this idea if we look at outcrops along some of the deeper gorges in the park.
Along this stream bed south of Eagle Peak toward Silver Brook, the sandstone exposed in the trees high on the valley walls is underlain by a softer, siltier rock, shown as slabby layers toward the bottom of the hill. This slabby layer is a silty sedimentary rock. Another place to see this silty rock is the waterfall near to the trout hatchery. These rocks suggest a calmer, deeper water ocean environment than that in which the sand was deposited, maybe in a bay. There are other important clues up another canyon.
This canyon is near Interstate Park Skyline Trail, and it has this amazing rock outcrop in it. I'm standing on basalt bedrock right here, and above me you can see the flat-lying Cambrian sandstone. But between these two rock units is this very jumbled zone.
This jumbled zone actually contains many basalt boulders, some very rounded. The local name for this boulder bed is the Mill Street Conglomerate. Between the boulders is fine sand. What could break up and round these hard lava boulders? One place we see this happening is along a steep cliff assaulted by storm waves. A good modern example is Split Rock Lighthouse on Lake Superior. Notice the cliffs and the boulders just out on the water. This cliff experiences strong wave action during storms. The boulders in the lake could eventually form a rock very much like the Mill Street Conglomerate. The powerful waves pound off basalt fragments and roll them around. Between storms and calmer weather, sand would sift down between the boulders. Notice how the boulder layers grade laterally to sandstone beds.
This direction would be further out to sea, and in this direction you'd find the old sea cliff from which the basalt boulders were being pulled by the strong storm waves. That cliff isn't exposed in the park, but there are basalt outcrops further upstream that would have been part of that old basaltic island.
Also notice that the boulders grade upward into sandstone beds. This shows the sea was slowly rising, eventually covering the cliffs as the boulder source is buried.
Reconstructions show that at the time these rock layers were being deposited 500 million years ago, Wisconsin was sitting pretty close to the equator and open to hundreds of miles of tropical seas. This is the perfect setting for tropical storms to come roaring in. What we see in mapping out the distribution of sedimentary rocks in this area is that the basalt stood up as islands in a slowly rising sea. And this sea featured a number of environments as it slowly rose up and covered the islands.
The sandstones such as we see in road cuts in Minnesota and around Eagle Peak were deposited as sandy beaches and underwater sandbars where wave action was moderate. The silty rock we see exposed under the sandstone in the deeper valleys would be deposited in deeper bays between islands. The boulder beds of the Mill Street Conglomerate would form along high cliffs open to the seas that experience pounding waves.
So if I was sitting here 500 million years ago, I'd be at a seashore, maybe watching the skies for an approaching tropical storm. This seems to be an amazing bit of reconstruction, but the evidence is all here in the rocks for anybody to see. It's no wonder that Interstate Park is a mecca for geologists and geology students to come study. You have erupting volcanoes, rising seas, the grinding glacial action, and the swirling river that will produce this wonderful landscape, all exposed for anybody to see and understand.